problem, and we talked about the types of problems that you might run into. And there are different types of problems that you could run into depending on how it's set up. So this is an interesting problem. I think we have Steph shoots a ball 30 feet from the basket. The basket is 10 feet up in the air. He releases the ball about 7 feet from the air with an angle of 30 degrees. Find the initial velocity so that he makes the basket. Okay. So as we're doing this, we have to know what we're given and what we have to find. And but the basics are still there. We're going to assume the regular gravity, and this is in feet. So let's go with the gravity as described in feet. There's no other sort of resistances happening. So I think we have all the information that we need. It's always good to draw your scenario if possible, and these projectile problems, it's usually possible to draw what's happening. And as you're drawing it, you want to set an origin, like where 0, 0 is supposed to be. So let's see. Let's have Steph Curry shooting the basket. Basketballs, are they usually bigger than your head or smaller? They're bigger, right? So that's your basketball. Shooting jumps up, I'm assuming. And here's the basket. So that's your general setup. And then let's identify some of the stuff that's given to us. We have, this is 10 feet. We are 30 feet away. Usually these things aren't drawn to scale, so that makes it even more important for you to be able to label. This is 7 feet. And then this is going to be released. An angle of 30 degrees from the horizontal with a specific speed, where the specific speed is the speed that we don't know. I'll call it V sub 0 without the arrow to let you know that it is a constant. And I think that's what's given. Okay. All right, now from here, we want to set up the math part, right? So the acceleration is going to be a vector, and there's no wind blowing side to side in this scenario, so there's nothing in the x-axis to worry about. And then the gravity is pulling down, and again, it's in feet, negative 32. And then we can label this if you want with the appropriate units. And then we work from here. Well, before we do that, let's establish the origin. I said to establish the origin from the beginning, and I forgot. So let's assume that this is the origin. That way we can try to identify all the different places that we need to identify. So let's say the ball over here is initially at the point 0, 7 feet high, 0. And let's call this R sub 0, because this is where everything starts. It's also good to know what this basket is, where this is. and this is going to be at the point 30, 10. All right, 32 came from gravity. Came from gravity, whatever system that is. Okay. All right. So I guess also as we're getting started here, we probably should identify a couple of important things. One of them is here that's already identified. R of 0 is equal to 0, 7. That's our starting point. Now V of 0, the vector, we want to be able to describe this as a vector. And remember, I want us to distinguish the V with the arrow versus the V that does not have an arrow. And the V with an arrow is a vector. The V that does not have an arrow is a scalar that describes the speed in which this ball is going to be projected. And whenever we're given an angle of inclination like this, we're going to use that cosine and sine. You can work out the x is the cosine and the y is the sine by using the triangle stuff. But we've seen that enough times that I hope it's going to be kind of semi-natural for you. So we know the values for cosine of 30 and sine of 30 degrees. What is it? 3 pi over 2 and pi, or 3 pi over 2 and 1/2. So we can do that now or later. I think this is a 3, not 3 pi over 2. What was I thinking? Root 3 over 2. That's what I wanted to say. So this will come in handy for us to plug those in later. All right, we have our initial position and initial velocities. And so from here, we can work out our...
Remember, what do you mean?
We can work out our velocity and position functions. So to get our velocity, we would integrate, and I'll put a little integral symbol here, d dt, or integral dt. And then we'll get our velocity function. And remember that if we're integrating, if we're doing an indefinite integral, we're going to have constants popping up. Let's call this constant C1. And then this is a negative 32t plus another constant C2. And to figure out what C1 and C2 are equal to, we can set the t equal to 0 and get our initial velocity. So V of 0, the vector, is equal to the initial velocity, the vector. And this vector, when t is equal to 0, is going to be C1 comma 0 plus C2. And our initial velocity is the unknown V naught times root 3 over 2 and 1/2 V naught. So C1 and C2 must equal to root 3 over 2 V naught and then 1/2 V naught. So we can conclude that our velocity function is going to be root 3 over 2 V naught in the first component plus or comma negative 32t plus 1/2 V naught. Okay. All right, from here we go one more time. So we'll integrate one more time to get our initial, or not our initial, but our position function. And for the first one, we have a constant with respect to t, so it'll be that constant √3/2 v naught times t. Plus, don't forget that there's those constants, arbitrary constants that pop up. D1, since I already used c. And then -16t squared plus 1/2 v naught times t plus another constant d2. Well, just like before, your r of 0 is going to be just d1 and d2. And this is supposed to be equal to r sub 0, your initial position, which, if you remember, was the height of the ball from the top of the origin where Steph let it go. So our d1 is equal to 0 and our d2 is equal to 7. And then now we have our position function. That's √3/2 v naught times t plus 0, comma, -16t squared plus 1/2 v naught t plus d2, which is 7. All right. So between the velocity and position functions, we should know everything about this particular projectile. We should know the maximum height. We should know when it hits the ground. We should know if it actually goes into the basket. So to answer the question that's being posed, does he make the basket? Or not does he make the basket, but what should the V naught be equal to so that he makes the basket? So we will note that the basket is here at 30, 10. So the basket is at the point 30, 10, and that's a position, right? So we just want the positions to be equal to each other. So we will have a couple of equations to work with. √3/2 v naught times t is equal to 30. That's the x component. And then -16t squared plus 1/2 v naught t plus 7 is equal to 10. So two equations and two unknowns. We have the time, t is the unknown, and the velocity, initial velocity v naught is unknown. I guess I should say speed, initial speed of the velocity vector. And we really just care about v naught, so we can solve for t in this first equation, plug it into the second equation, and then eventually just solve for v naught. Or you can solve for both of them if you want. And then that'll tell you how long it'll take in seconds, how long it'll take to make that basket. So let's, for now, solve for just t in this first equation. T is equal to 30 over v naught. Now this is going to be the reciprocal. The 2 would go on top, right? And then the square root of 3 would go on the bottom. So that's, what is that? 60 over v naught √3. Okay, let's plug that into the second equation. -1660 v naught √3 squared plus 1/2 v naught times 60 over v naught √3 plus 7 is equal to 10. I think there's some v naughts that cancel. Let's see, how many things can we cancel? We got the v naughts we cancel. We can get rid of 1/2 of 60. Over here, we get 60 squared. This is gonna be V naught squared. This is gonna be root 3. So maybe I should really be careful about this. This is 60 squared, that's 360. And then root 3 squared is just gonna be 3. And so this simplifies to 120. So that's what I'll get. Oh, thank you. Another 0. Come on. Oops, not that 0. The 0 over here that got canceled. So who was that? Thanks, Ecom, for catching that. Okay, let's see. So this is 1200. There's a negative 16 still here, times 1200 over V naught. Let's see what happened here after we got things canceled and worked out. This is a 30 over root 3. And oh, this is a squared, V naught squared. And then let's bring the 7 to the other side. So this will become a 3 here. And then just solve. Should I keep doing this by hand? Yeah. Okay, so let's bring this over to the other side. Negative 30 over root 3. Common denominator, square root of 3. So this is negative, should I multiply this in my head? No. 160.
19,200 negative.
Negative 19,200.
200.
Over V naught squared. And this, I will call this a 30 minus 3 root 3, negative 30 plus 3 root 3 over root 3. I want the reciprocal. Can't believe I'm doing this by hand. This would be root 3 divided by negative 30 over 3 root, or times, or no, negative 30 plus 3 root 3, and then reciprocal, this goes in the numerator, negative 19,200. And I see that this is negative 30 minus something smaller than 30 is going to be negative, but then this will make it positive. So V naught will equal to, there's plus and minus, but of course we'll take the positive part, the square root of 19,200 root 3 divided by, and then switch the order. 30 plus 30 minus 3 root 3. All right. Fun with algebra. Anybody got a value for this?
36.616.
36.616. So this is the velocity. So you can say that so Steph has to shoot with initial speed of 36.616 feet per second. That's it. All right, so that answers that question. Let's ask a few more questions. Like, what is the maximum height? We can ask about the speed when it goes through the basket, or when will it go through the hoop. And then how fast the ball is going as it goes through the hoop. All right, let's ask this one first, or let's answer this one first. Why is there a question mark down here? Nope, that's a phantom question mark. All right, let's answer some of these questions. When will it go through the hoop? There's a hoop. And how fast is it going? So when is a question of time, and I think at some point here we solved for t going through the hoop. So if we know what t is equal to 60 divided by v naught root 3. And we have v naught, we found v naught. 60 divided by 36.616 times root 3. And what's that equal to? Make sure you put the parentheses around the denominator.
2.8382.
2.8382 seconds. So it's a 2.5 to 3 seconds from his hand to the basket. Does that kind of make sense? Takes about that long, right? And the buzzer goes off. Bzzz.
I think I made a goof.
Yeah, 'cause I got 0.946.
Yeah, I thought it might be smaller. Yeah, Ecom got 0.946 also.
I just didn't trust myself to make this, I think, tiny error. So I was like, maybe I am just wrong again.
Well, that's why we have more than one person to check. What was it again? 0.9.
461.
0.9461 seconds. All right, if you want to know how fast it's going as it goes through the basket, what do you need to do? Yeah.
The velocity.
Take the velocity,
Magnitude.
magnitude of the velocity is the speed, right? So magnitude of the velocity, and then you put in the time that we got. Good. So speed is the magnitude of the velocity at this given t naught, or t1, maybe. T naught sounds like it's the beginning. So we need to find the velocity and take the magnitude of that. This is our velocity. Oh, we have our V naught as well. Oh, this is getting to be too much for me. I don't want to do this anymore. Root 3 over 2 times V naught. Root 3 over 2 times V naught, which is 36.616 squared plus negative 16, negative 32. Negative 32t come on. 32t, t was about 0.9461, negative 32t plus 1/2 v naught, 36.616. And then we have to take that and square that. Oh, I really don't want to do this. So whatever this is, approximately equal to. All right. If y'all want to figure that out, go ahead. But let me start addressing our next question. What is the maximum height? So how do you suppose we find the maximum height? What can you say about the maximum height?
The velocity would be 0.
Okay, so let's be clear about that.
In the y direction.
So the velocity in the y direction goes positive, at some point it comes negative and it goes down. So the velocity at the y direction is equal to 0. Find the time. So set y velocity equal to 0. Solve for t to get the time. And then once you have the time, what do you do once you have the time? What do you do with that time? Let's call it t2.
1/2 gt squared.
Well,
1/2 thing doesn't always work.
yeah, the 1/2 thing doesn't always work,
Yeah.
It does work.
especially when you're 7 feet, you're starting off 7 feet from the ground.
The moment you start
It
to
is.
adjust the.
It is a difference of height. You can add 7.
What?
To find the actual height. So you're 7 feet above the sea level, for example, and you find the difference of height and you add 7 feet above the ground.
But
And
what
that's
do you
the
do
actual
with
height.
T2 is guess what I'm asking.
So for T2, v equals gt. You can put it in for the position function. Oh, all right. I'm doing
Just plugging it into RT would be perfect. Thanks, Yukam. So
It's not like position.
Plug it in, it's like.
So plugging it into RT will not only give you the X value, but the Y value as well. Which one of those do you want for the height?
Why?
Okay, that's it. Now, I won't do it algebraically, but let's take a look at the graph of this. Because we can. And let's first set up this with the position function, because that's what we want to see with some random V naught that we don't know yet. First, let's set up all the initial stuff. So what are the initial stuff? The initial stuff is the starting point is 0, 7. And the basket, the hoop is
and
10,
30, 10.
30, 10. So this is just going to look like a point. If you want to make it look like a basket, you can make an ellipse or centered around that point that's a little bit wider. I don't want to get too fancy with that because that'll just be a time sucker. So here's the starting point and here's the ending point. The function itself, if I remember, was root 3 over 2 times V naught comma, wait, this is the position, so I need to multiply by t times t, comma, negative 16 t squared plus 1/2 V naught plus 7. So if your V naught is equal to 1,
Wasn't it half V naught T?
oh. What? 1/2 V naught
Half V naught
T, yes, there's a T in here. Plus 7, I put 7 in the wrong spot. There's all kinds of wrong. So this is pretty sad airball. If he throws it like 1 foot per second. So if he throws it 10 feet per second, he'll get this far. So we want, I think we went all the way up to, what was the answer eventually? 36. So let's go to 40 here. And let's start from 10 to 40. So you want this to go and reach this point, and 36.6 seems like it's the correct velocity. All right, and now to find the maximum height from here, we didn't actually solve for it, but it looks like, oh, I can't trace it. Usually I could just put a little dot, maybe let's say x equals t sub 2. What? Let's just say a then. What? Okay. Where's my slider? I want a slider. B. How come I don't have a slider?
Since the position function is the derivative of the velocity function, can't you just put in the y component of that and find out where it crosses this x-axis to find the part where the velocity function is 0 because it's the tangent?
Yeah, well, that's the thing, is that we didn't solve for when the velocity function is equal to 0.
Well, yeah, but I'm saying by using the derivative of the position function, when you plot the y component of it.
Oh. This thing?
Or the RT function. Sorry. Oh wait, never mind. No, sorry.
But I could plot this.
Yes, yeah, that's what I mean. Yeah.
That's a neat little trick. Well, I don't know if it'll work. Let's see. Square root of 3 over 2 v naught, comma, negative 32 t plus 1/2 v naught. Uh-oh, that's weird. I don't know if that worked. Yeah, maybe not. Well, we didn't do the work, and I was hoping to just find it by just kind of, let me see, kind of fiddling around here. There's my slider. I don't know why it wouldn't happen to make the slider before. So this is my point. Let's draw this point. This is in blue right now. So right around here is probably the maximum. So if we solve for that, we get about 5.8. And then if we put 5.8 into the position function, this is our position function. And if we put A in there, we got the maximum height of about 12.23. I think he shoots with more of an arc. Maybe I should have done this where the angle was 60 instead of 30 degrees. This seems pretty flat. Anyways, that's the story with this. Any questions? So that's our two-dimensional example, and this idea of finding the maximum height where you have to set not the velocity equal to 0, but the y component of the velocity equals 0 is going to be important for us. Okay, let's do another example. So here, suppose this is actually one of the honors projects from last year. I'm taking it out and changing it. So here you're supposing that you're in a helical roller coaster traveling on a specific path. And the path is going to be this 10 sine pi times s, 10 cosine pi times s, and 3s. So we're in feet again, so we'll keep that in mind. So 3 seconds from the starting time, you're taking a selfie and then your phone slips out of your hands and goes flying. And so as it goes flying tangent to that curve, right? So it just flies up somewhere, and I'm assuming you're going upward. So as the speed of the roller coaster is going up in this helix, you let go of your phone and your phone goes flying out. And then from there, you want to track your phone, when's your phone hit the ground and stuff like that. And then there's another example, or there's another part of this problem where your phone can take a hit of some speed when it hits the ground before it breaks. And then you ask yourself, does your phone break? Supposing you have like an Otter phone case or something. All right, so that's the general idea. There's a drawing here already, but let's redraw the situation. You're flying off. At some point, your phone flies off. And so you have to establish your initial velocity and your initial position from this point where the phone flies off. And then from there, your phone will go through a projectile that acts only on gravity. Maybe we should put wind blowing here. Should we put wind? No?
Air resistance.
Okay. I mean, if you're in the ocean, right, it's windier. I don't know where this roller coaster is though.
Space.
Have you guys seen a roller coaster shaped like a helix like this? Well, it must exist somewhere.
Is that a vacuum chamber?
All right. So basically you want your friend to run to that spot to be able to catch your phone. Okay. Let's start. Find an initial position and initial velocity the instant that your phone flew off. So I know that there's already this equation here, or this function that's describing the roller coaster, but that is actually going to be that's going to help you find your initial position and your initial velocity of your phone once it flies off. So it turns out that the position, initial position, and I'll call that little r of sub 0, and we'll just call the phone's time parameter as t, and then the roller coaster is just s. That's not a big deal. Is going to be equal to the time or the position of the roller coaster at the time, at the time that they gave you. So that is r of 3. So what's sine 3 pi? 0. Cosine 3 pi? 2 pi, 3 pi, -1, -10. So it's -1 times 10, and then 3 times 3 is 9. All right. So your initial position for the phone would be 0, -10, comma 9. And now the velocity initial velocity will actually be the velocity of the roller coaster at s is equal to 3. So we need to find the velocity. I'm going to write capital V, try to make it capital. So we need the derivative of that. So the derivative of r, this is a vector. Oh, maybe I can write r prime s, and that's equal to positive 10. Oops, there's a pi. Cosine pi s, comma, this will be negative. -10 pi sine pi s, and then this is just going to be a 3. So let's put 3 in there. So cosine of 3 pi negative, -10 pi, sine of 3 pi is 0, and this is just a constant 3. So there we go, initial velocity for the phone, -10 pi comma 0, comma 3. All right, so now you have information about your phone, and with the gravity, you can figure out the velocity and position functions. Remember now that this is three-dimensional, right? So your acceleration is going to be 0, 0, negative 32. Right? Because it's three-dimensional, the z is going to be the height, and that's where the gravity comes down on. So that's important. We integrate once, get the velocity, and that's going to be c1 comma c2 comma negative 32t plus c3. And then if we put 0 in there, we're going to get the position or the initial velocity of negative 10 pi 0 comma 3. And if you put 0 in there, you're just going to get c1, c2, and c3. So your velocity function will equal to negative 10 pi comma 0, comma negative 32t plus 3. All right, so this is an integral step. Now we integrate again, and you get your position function. Negative 10 pi times t plus a constant, we'll call it d1, d2, and then negative 16t squared plus 3t plus d3. And again, your initial is given to be 0, negative 10, 9. And that will end up being your d1, d2, d3. By the way, if your acceleration are all like constants or even polynomials, then when you solve for your initial conditions this way, it'll be whatever your constants or whatever your initial conditions are. If for some reason your acceleration has a function like a sine or a cosine or an exponential function, something that's not automatically equal to 0 when you put 0 in there, then you would actually need equations to solve for your initial conditions. Okay? And I suppose that can happen if you're the projectile being thrown off and then you have a rocket packet or a rocket attached to you where your acceleration blows you around at different times. I don't know. I had a problem like that once that I made up. Anyways, your position function finally is equal to negative 10 pi times t plus 0, comma, negative 10, comma, negative 16t squared plus 3t plus 9. All right. Again, you have your velocity and position functions with the velocity, with actually just the position functions, because you can always just take the derivative. With the position function, you can figure out what's happening with the rest of your problem with your projectile. Like I didn't ask for the maximum height, but you can certainly find the maximum height this way. But the question is specifically they are asking for the maximum height. Never mind. Why do we switch variable s to t? S was the variable that they decided to use for the roller coaster. And I guess they just used S to make it different from our new timeline for our phone. Our phone will have a time of t and your roller coaster will have the time of S. Okay. All right, let's find the maximum height. You find the maximum height by setting the derivative equal to 0. The derivative has 3 components, right? So you have to make sure that you set the appropriate component of the derivative equal to 0. So part C, max height. Set Z component of V of t equal to 0. I'll say equal to 0. So this one's easy. I got negative 32 t plus 3 equal to 0. So it becomes negative 3. And with a negative 32, it becomes positive 3 over 32. That's not very long. And then plug it back into the height, the position height. So not just the position function, but the z component of the position function. So the z component is just negative 16 t squared, so that's 3 over 32 quantity squared plus 3 times 3 over 32 plus 9. Doesn't look like it goes up very high. Anybody got a value for this? Ish.
$9.14.
9.14? Yeah, I think so. That's not
I mean,
very confident.
parentheses can be fiddly with these calculators. Sometimes they do a little bit of PEMDAS and sometimes they're just like not at all.
Well, you have to put parentheses around the non-PEMDAS situations, so. Okay. Where does this happen? So if you take this time, wait, this isn't the time. Oh, this is the time, and this is the height. So if you want the x and y component of that height, you would just put it into the x and y component of the position, which it looks like it stays t, the y value stays at negative 10, but then the x value would be whatever that is. Okay, let's go to the last one, hit the ground. So that's just simply z is equal to 0. So in the position function, we'll set z is equal to 0. So it's negative 16t squared plus 3t plus 9 equals 0. And then you'll get a time out of this. I don't know, quadratic formula or something. Okay, negative 3 plus or minus the square root of 3 squared minus 4 times negative 16 times 9 divided by 2 times negative 16. So I'm assuming one of them is going to be completely negative, the other one hopefully is positive. So the question is that when does it hit the ground? And you'll get the answer here. And then you can also follow it up at what point, where does it hit the ground? So you need to plug it back into, well, when you plug it back into the third component, you should get 0. And then you just plug it back into here, -10 for the y, and then -10 pi times whatever value you get here. Somebody figuring it out? Nope, nope. Ecom's gonna come up with it. All right. As you're all working on this diligently, I was gonna say hardly. Are you working hard? Hardly. It should be probably a little bit more than 6/32. Anyways, plot 3D. We need a couple of space curves. One of them is a 10 cosine pi times t, 10 sine pi times t, and 3t. I know they said s, but you know, when we're graphing things. I want to go from, we're taking off at 3 pi, so I guess 10 would be fine. 3 pi is about 9 point something, right? I think I need to zoom out. There it goes. So that's the roller coaster that's happening. Zoom out more. Well, maybe 10 was too much. 3, no, it just went 3. So let's go 4. So something like that. The initial position we got was, what was the initial position again? Was it -10 or 0?
-10,
0, -10, comma 9. Well, there's that point right there where, ooh, how come it's not on the curve? Three times 3. It's not on the curve. What's happening? Uh-oh, I'm freaking out here. What's happening? Oh, wait. Oh. Oh, it's sine first. Dang it. Sine and then cosine. Oh, wasted that time. There he goes. All right, so that's our starting off point. The velocity vector. The velocity vector is -10 pi 0 3. -10 pi 0 and 3. but we want it at this point. So that's your velocity vector. And then we don't have time anymore, but if we were to graph, this position of the phone, we'll see the path of the phone, and then we'll see it hitting the ground, and then you can use the graphing program to estimate what this quadratic formula is. That's what I wanted to do, but we don't have time. All right. All right. So I want us to think about the theory things, ideas that we're talking about, like what the set equal of what when you're looking for the maximum height, when you're looking for when it hits the ground, when you're looking for when it hits something in our projectile. Those are some of the types of questions that you're going to come up with in the theoretical portion. So it's knowing the difference between if you have a 2D or a 3D graph situation, that should help you think about what's the height? Is it the Y, or in 3D it has to be the Z? And then what's the position of the distances and things like that? Okay, I think that's it. I'll put in the rest of the solutions here, but I won't finish the graph, so you guys can view it yourselves or make it up yourselves. That's it for today. Tomorrow there's no class, and we'll come back here on Wednesday to start chapter 4. Good luck on your exams. Okay. Bye, Fabian. Bye, Eric. Brandon. Have a good day.